Start recording and ask you, what do you remember from last time?
I wasn't sick.
You weren't sick last time? That's a good thing to remember. I've got a list of topics here, but I'll take words, gestures, letters.
Tau?
Tau. Okay, tell me about tau.
It's a Greek letter.
It is a Greek letter.
Wasn't that used to indicate the variance for the level 2 factors?
Yes, it was. Tau squared is
sorry.
yep. It's since it's a variance, it's squared. Although that's
Yeah.
not every author does it that way, but that's the most common variant.
That's common.
Yeah. Tau squared is our abbreviation for the variance of the U terms, which are called what? Two-word phrase. The first word starts with an R. Not as helpful as you would think. I know a lot of R words that sound like they could work.
It's not recursive because that's the other class.
It's not recursive. Nope.
Random intercept.
Hey, nailed it. I would also accept random effect as a more generic term because effect is like the overarching umbrella under which intercepts and slopes are particular kinds. But intercept is the more specific good definition. Good. Conceptually, what is a random intercept? What's it for?
Adjusting between clusters, help adjusting between clusters, I think.
Yeah, it's the idea that a naive starting point for a prediction should take into account the cluster that a given person is from as part of that. And so U0 then is a deviation from the grand mean. I think this is a good place to hop in here maybe with a picture or two.
Pictures are awesome.
I like pictures, yeah. This is slide 6. Let me make sure it's being captured. Okay, yes, we're good. So we have, this is the equation that goes with the picture. Okay, so pretend like we have people from a green cluster, people from a yellow-orange cluster, and people from a purple cluster. So the red line is meant to indicate the overall sample average. So this would be like the mean of the cluster means, and that is given by beta 0, which is called what?
Intercept.
Yes, one more word before it. Starts with an F. Yes, we have to differentiate in this class. We have to say fixed or random in front of things because it matters which they are. So beta 0 does not have a P or C subscript, so we know it's not a variable, it's a constant. So fixed effects are constants that apply equally to everyone's prediction. From there, U0 captures the discrepancy between the cluster mean and at the fixed intercept, which is the grand mean. So how far off your cluster is. So U0 has a mean of 0 because the mean is over here as beta 0 instead. So they work together to describe the overall cluster mean. So the purple U would be positive or negative? Throw a few softballs out here. Negative. And the green U would be positive or negative? Positive. We got it. So vocabulary that goes with this, U0 is a level 2 term. It is a cluster thing. Some textbooks will call those level 2 residuals. I'm not going to do that to you. It's going to be level 1 for residual and level 2 for random effects. They capture between cluster differences in these means. So why are some clusters higher or lower on average? We don't know, but cluster characteristics can help to explain why that is the case. Intercluster differences. From there, E captures the remaining discrepancy to the individual's outcome. So people who are higher than the rest of their cluster would have a positive E, and people who are lower than the rest of their cluster would have a negative E. And E variance is sigma squared sub E, like it usually is in regression. So these are level 1 residuals that capture within cluster or between person differences or intra-cluster. I tend to stick with within and between as labels as opposed to two different kinds of betweens, but that is a choice that you can make. So level 2 is between always, level 1 is within always. The question is between or within what? In this class, it's clusters. In longitudinal data, it could be persons, for instance. Okay, how are we doing? Yes.
So maybe I'm thinking of a different model. Where would you put the average, if you would put the average of all the original data? So this is the mean of the cluster means. It's not the mean of the original data.
That's right.
And those are completely different animals.
They can be.
Unless of course they're equal size clusters.
That, yes. So if each cluster has 10 people in it, then the mean is the same thing as the mean of the cluster means.
Yes,
But-
but if it's not, then what?
So what happens, and we'll see this in our example, is that if you leave out this random intercept right here, meaning you take the random intercept variance out of the model as an estimated parameter, beta 0 then is just the straight up mean of that overall column.
Okay.
So the weighting happens once you introduce the idea that there is level 2 variation, that this is the centerpiece of. Okay. Cool. Thanks for the question. Other questions? Or the things you want to hear again or differently? Would I say that we have explained any outcome variance at this stage? I would not. Why not, Mubarak? Yep, we are partitioning or decomposing or splitting, whatever word you want to use, the idea that we have two separate piles of variance now. We know that some clusters are higher than others because there's variation across clusters in the means. We don't know why. We need cluster characteristics to try to answer the why question. Likewise, we don't know why people from the same cluster differ from each other. We need people characteristics to be able to answer that question. Good. All right. Then we were here, and I promised we would re-go over this, right? Okay. Keep my promises. So this is the same model as this. We're just switching the notation around a little bit to use a hierarchical system. This is not done everywhere, but I find it useful, and it is common within social sciences. It's less common, I would say, in like the biostat or the stat world. But we switched notation from a single level model. I had a beta 0 here. Beta 0 is now going to be used for something else. This is beta 0 C. So adding the C tells us that it's what? It's a cluster thing. Yeah, it's not a constant anymore. So this is now a variable that varies across clusters, beta 0 here. And this is how we get beta 0. It is built from two pieces. Gamma 0, 0 is what we're now going to use for what was beta 0 before. Gamma is this Y-looking thing right here. It's not Y, though. Gamma, another Greek letter. That is going to be our fixed intercept. And this is the mean of the cluster means in this case, because this is still technically an empty model with no predictors. All we have is two different piles of variance in the model for the variance, nothing in the fixed effects. So U0C is, again, how far off your cluster's mean is. So it's off from the fixed intercept. So that brings us to a rule that you will learn. You can have fixed effects only, and you can have fixed and random effects, but you cannot just have a random effect without the corresponding fixed effect, because the fixed is the center. And if I were to leave this out, then I'm assuming the mean of the cluster means is exactly 0. And that doesn't make any sense. And it would be something that you need to estimate even if the mean were close to 0. You don't want to zero these out. So we have a fixed something. We add random variation around it to create the variable. Otherwise, we just have this as a constant. So beta 0C, I call these placeholders. I call these backpacks because they're carrying the fixed and random effects within them. You can also think of these as latent variables. So SEM carry crossover, I'm always going to do that. This would be the mean of the latent variable, and the variance of it would be the tau squared. It's this thing. So putting it all together, this model has three estimated quantities. A fixed intercept, which is the mean of the cluster means, a random intercept variance, which is tau squared here, which is the variance across the cluster means, and then sigma squared E, which is the variance across the people, assumed to be the same across clusters. Both of these things are. There are models that extend that, so they're not the same, but we're not going to get a chance to get there. Bummer. And the composite notation would look like this. So in linear regression, I start with an empty model for pedagogical purposes. And by the end of the semester, I tell them, you would actually never do this. I just wanted you to get started with the idea that there's all this variance in total that we gradually reduce. And seeing how much there was to begin with is a useful pedagogical thing. In these models, we absolutely do this. Like if you're doing a multi-level analysis, this is step one no matter what, because you have to know how much variability you have of each kind to know how to proceed, as well as testing additional sources. So I think you had asked me about this last time, like, are there other kinds of clustering that you can have? Yeah, you may find that there are additional sources that were introduced without, your blessing or your permission, but you still got to deal with them. So finding out how much variance and what kinds is always step one. We do that so we can report a descriptive statistic that goes by the name of intra-class correlation. You have maybe heard of this phrase before in the context of assessment of reliability. It's a measure of reliability when you have like multiple raters and multiple targets. ICC also stands for item characteristic curve over in IRT land. Sorry, it's the same letters, it just serves multiple purposes. In certain disciplines, you will see this as ICC1 in particular. There's a 1 and a 2 that are commonly reported, but this is the one that everyone will report. I've written it out 3 different ways. It is a ratio of how much of the variability is due to between cluster level 2 random intercept variance divided by that plus the remaining variability due to level 1 residual variance. So this denominator, if you were to fit a model with just E in it without U, the denominator should be pretty close to what it is here. Like the total variance that was in E is split into 2 piles, that's this denominator. Not exact, because unless the clusters all have the same sample size, but close. So this statistic, you can interpret 2 different ways. The first one I think is more transparent. It's the proportion of total variation that's between clusters. How much of your variation in Y has to do with what school you go to, what company you work for, what instructor you have, etc. You can also think of it in a correlation metric as the correlation among people from the same cluster on average. So how correlated am I with other kids from my class or from my school? This one I think is a little less intuitive because you're referring to a within cluster correlation as a concept, even though the numerator is between cluster variance. So I think I have a picture about that. Yes, I do. Okay, thought I did. So another way you can think about this that's related is that word dependency. Remember that word from last week? Dependency? Pretty sure we talked about this. What's it mean? If I have a dependent data outcome, what's it mean? Starts with a C. I'll take a synonym for it. CO.
Correlated.
Hey, yep, correlation. Yep, dependency is the idea that the residuals, in particular, from the same cluster are going to be related to each other. We don't know why, just they probably are. The extent to which that occurs is captured by the ICC. So the ICC can be considered an effect size for how much dependency there is due to cluster mean differences in your data. Non-constant cluster dependency is created by random slopes instead of just a random intercept. We'll get to that in a couple of weeks. And just as a reminder, we're not explaining variance. We're just figuring out how much we have of each kind. So this ranges between 0 and 1. Based on the formula, what would 0 mean?
Why bother between?
Why bother between?
I mean, if it's 0, there's nothing between. You might as well just have just one level.
Yeah, if the numerator is 0, to create an interclass correlation of 0, that means there's no between cluster mean differences. Adding a random intercept to the model didn't help, and we're going to deal with how we judge that in just a second, but you can test empirically the extent to which adding a random intercept variance helps your model. So yeah, if it's 0, then there's no cluster dependency. However, what's going to happen is anytime that you explain level 1 residual variance, your level 2 random intercept variance is going to increase. It is a logical consequence of the way that they are estimated. We'll talk about that later on too. So that means that the more level 1 predictors you add that do a good job explaining people differences, the more between cluster differences can emerge, even if they weren't there in the first place.
So do not base it off of your empty model.
That's right. There is no intraclass correlation that is really safe to ignore until you've gone through all the steps in your analysis. If it stays 0, like no matter what you throw at it, cool. That means like if you randomly assign people to clusters, for instance, random assignment worked. That's what that would mean. And in some contexts, that's what you want. All right, so the correlation thing, think of it this way. So this is the picture that I had earlier with the very distinct groups. In this case, the differences among these cluster means are large relative to the differences within the clusters. So this would create a very large interclass correlation, like 0.8 or something would be, that's one of the largest I've seen. That doesn't happen in cluster data, but it would in longitudinal data. And from a prediction standpoint, if you think about correlation as prediction, like if I know this purple person's score here, a high ICC means that I have a really good shot at predicting any of the other purple people's scores. They're highly related to each other. There's not a lot of within cluster variability. It's all between clusters instead. In contrast, if I had a picture that looked more like this, then relatively speaking, the within cluster differences are much larger than the between cluster differences. This would yield a small interclass correlation. So like if I know this purple person's score here, I don't have a very good shot at predicting any of the other purple people's scores because they're not very highly related to each other. Now I have a song in my head from my youth. One arm, something flying purple people eater. Do you have any idea what I'm talking about?
Yes, I know
Okay,
this.
ask the Google about this. It's a song. Flying purple people eater, one-eyed, one-arm, flying purple people eater. There we go. Purple people. And I'm not even on caffeine right now.
Unshaken?
No, this is a flat soda from last week, so I wasn't going to have an incident anymore. But yeah, I actually prefer flat soda. I'm weird like that. Just one of my things. So, all right, does this make sense? Interclass correlation as a ratio that tells you how much of your data has to do with clustering. It's an effect size. So here is a slide that was from a workshop, so I just left it in here. This is what code for an empty model would look like in a variety of packages. SAS proc mixed, where proc stands for procedure. In R, for this class, we're mostly just going to use a function called Elmer. It's from the LME4 package. That's because we don't have to worry about differential residual correlation in the context of cluster data, so we don't need to deal with that. So we just have this little formula right here. Stata, we're going to use mixed as well, and SPSS has a routine called mixed that is largely ripping off proc mixed from SAS in its structure, although the colors are different. So so I gave a workshop for APA over spring break that year in 2023, and I had made brand new slides for that, and so this is from there. The rest of those materials, if you're interested, are here, and I believe those videos are still up. So if you need like a quick and dirty introduction to clustered multi-level modeling, there's an hour and a half each day, I think, something like that. It was fun. But this is the example that I used for that little workshop, so this is different than example 2 that's in your handout. I wanted you to have, I think, 2 different sets of data to work with. So this is from the Snyders and Bosker text, which, by the way, should be in, I think, at the end of this week is what was predicted, if you want to check out the paper copy at the library. I have 3,500 and so students, so they're going to be my P units of people from 191 schools, or as the cluster. We're predicting language outcomes from an empty model. So language PC here, EPC, because this is per person per cluster, and then at level 2, any variables just have a C's because they're just for cluster. So without the random intercept in the model, so if I take this thing out, here's what I get back. I get a fixed intercept of 41.46. That's the mean language score in this sample across all the people. And then I have residual variance of 77.7-ish. Don't pay attention to these things. They don't show up on any other software package that I'm aware of. This is a walled test as to whether that variance is different than 0. We don't pay attention to those because variances are bounded at 0. So the null hypothesis is on the boundary. Variances can't go negative, so a walled test that has 2 sides doesn't make any sense. So we're going to do something else to decide whether variances are significant. We would ignore that. R doesn't even give it to you. With the random intercept, though, we get slightly different numbers. So the mean went from 41.46 to 41.08. So not a big difference, but just a little difference. Do you remember why that is? The question we had about 10 minutes ago is why. It's a callback. If the random intercept is in the model, this has a different interpretation. Who's feeling brave? Nobody's feeling brave. Hey, TAs, you're up.
That would be the sample mean, right?
Yep. So this is the sample mean over here, right? On the left. Erica, what is it on the right? It's the fixed intercept, but what does it mean differently over here than it does over here? This one on the left is the grand mean. So we're asking about this one.
That would be the
Cluster mean?
The mean of the cluster means. So it's a differential weighting. So these will be more discrepant when your cluster sizes are more discrepant. So we have school level variance in this data set. School ID is the cluster identifier of 17.8 and residual of 62. So we add those together and it's not quite the total of this, but it's pretty reasonably close. So just reinforcing the idea that we're just taking all unexplained variance, we're putting it into two piles. The interclass correlation that goes along with this is actually pretty strong for cluster data. 0.22 is what we have here. So this
0.25, like that the normal for strong, or?
no, like 0.1 to 0.15 in cluster data. You're nodding. Are you familiar with these?
Well, in management, a lot of what we do is teams. So
Mhm.
we talk a lot about ICC and especially individual differences. Even like a 0.1 explaining someone's behavior is a lot of explanation.
Yep. Yeah, and I imagine the context of what the variable is matters. So like if you're working in teams and everyone's answering some question about like their own self-esteem or something, you might have a smaller interclass correlation than if they're all answering questions about their manager's self-esteem, like they're all pointing to the same target. That would create a higher interclass correlation because it's really a cluster level construct that you're trying to measure with individual level data. So, yep, this is a little bit high. Let's see, in Rongsu's data, Vladimir, how high is it?
We have like between 2 and 3%.
2 to 3%?
Level 2 or 3. Level 1 is 97.
Yeah, so individuals are 97%, and then there's like 2 to 3% across time and across states.
Yes.
And these are career aspirations or something?
Yes, vocational interest,
Yeah.
which is a great finding for us because most of the analysis with this type of data is a level 2 thing. They
Oh.
aggregate data and they make analysis using state means or students mean. So
Yeah.
that's good for us.
So
Not
they're
for
throwing away 97% of the story, is what you're telling me.
Yes.
Well, that doesn't seem like the greatest idea to me, but what do I know? I'm not in that field, so. But 0.22 is what we have to work with. So let's say that I wasn't planning on dealing with individuals and I only wanted to deal with schools. If I only have school level predictors in my data set, what is the most variance I can explain in this outcome? It's a little thought experiment. Yep, if all I have is school level variables as predictors, the best I can do for an overall R square is 22.3%. Yep. Now what if in that case I chose predictors, thinking of a particular example in my head and deciding how I want to word it. Let's say that I evaluated a bunch of school level predictors and they turned out to be non-significant. Could happen, right? Sure. Non-significance is a way of life for a social scientist, but we keep going. Does that mean I don't need a multi-level model after all? You don't think so either? I got 2 votes for no. Does that mean I don't need a multi-level model, yes or no? Sure, go ahead.
So for ICC here, it's like putting true points ratios and a total numbers is excluding. So now it depends on the data. We cannot, sometimes like if ICC is higher, it's better. Sometimes it may not be good. Depends on the question. Or ICC is, if it's higher, it's always better.
Okay, great question. So just to repeat it for the recording, can we talk about ICC being high or low as better or worse? Essentially, like, is there such thing as a good ICC? Your instincts are correct. It absolutely depends on the purpose of the study and the question. So if I were really interested in school differences, in addition to individual differences, I would be pleased with this result because it means I have school differences to go and investigate. If I didn't want to deal with schools and I really wish that I didn't have any dependency and I just want to make it go away, then I want my ICC to be as small as possible. So the same logic that you would learn in thinking about experimental design applies here as well. If you want your ICC to go away, adding in school predictors to reduce that amount of variance reduces the interclass correlation and the dependency along with it, and it improves your power. So even if you don't care about schools, it probably behooves you to care a little bit so that you can reduce the dependency and get more power for your person level effects. But in this case, if I didn't have any significant school level predictors, does it mean I can just go back to single level regression? Got three or four no's now. I think we're converging onto a solution. You are correct. Just because we don't know why the 22% is there, it's still there. We can't pretend otherwise. And believe it or not, I once watched a job talk where someone did exactly that. They had a 3-level model and none of the level 2 or 3 predictors were significant, so they decided regression was A-okay. I had thoughts about that, but what I was most proud of, though, was I was actually not in the talk. I was sick that day, and my students from multi-level modeling told me about it in the next class, and they were like, they said this, is that right? I'm like, there's no way they said that. And I watched the tape, and I mean,
You verified.
like literally watched the tape because it was so long ago that it was on VHS recordings is how we got job talks to, and that's what the person said. But they said it in such a way that they sounded uncomfortable, like someone told them that advice and they didn't know whether they should believe it. So they just like that kind of language. So when we discussed the candidate, someone brought up their amazing stat skills, and I was like, actually, maybe not so much on that. And they're like, well, do you think that she's a problem? And I'm like, I don't think she's a problem because she's not being hired to be a statistician. But it sounds like she got some bad advice, is what I said. I think that's the fairest thing I can say. So just because you don't know why a variance is there doesn't mean you can ignore it. That's the take-home message on that. Sound reasonable? Okay. Other thoughts or questions? Please.
In our model, in the second red box, that 41.07, that's gamma 00, right? That's not BOC.
Correct. This is, like this would be, on this side it would be just beta 0, like a fixed intercept in a typical regression model. This is gamma 00 over here. It is not beta OC because it doesn't include the random effect that goes with it.
Lisa,
Yes?
we know that we will have predictors at level 1 and level 2, although that fixed intercept won't move to any other place.
That's right.
What I mean is, we know that the fixed intercept is conditional on the predictors in the model being 0, although in the formula it's always tied or linked to the BOC,
Yes.
right?
Yes.
But the interpretation is the same as in traditional regression. It's conditional on all of the predictors, level 1 and level 2 things being 0.
The definition is the same as in regression in the sense of it's when all the predictors are 0. So it's a conditional mean. But it's like the conditional mean of the cluster means because of the U0 part. And in normal residual data, like there's no discrepancy between, like if you would say what the mean is or the mean when random intercept is 0, but in generalized models there is a discrepancy. And that's where you get into unit specific as an idea. And that same discrepancy shows up in SEM. Like we would say that the fixed intercept is when the factor score is 0, meaning the factor score is this U0C right here.
Follow-up question. Sorry,
Okay.
Lisa, we are saying that the fixed intercept is the conditional mean of the cluster means.
Yes.
Right? But could we say, for instance, when we have students in schools, could we say that the fixed intercept is the predicted outcome for the reference student in the reference school? Considering
Yeah.
that the fixed intercept is conditional on all of the predictors being 0, including the level 1 things?
Yeah, it is setting a reference for the for the people and for the clusters. I would agree with that.
Yeah, to me that's confusing sometimes because if we say that it is the conditional mean of the cluster means, it seems that the level 1 things are not contributing to that prediction, but they are considering the general definition of a fixed intercept.
Yeah, so the fixed intercept is a level 2 thing, essentially. And so then the student variables would be level 1 things. And so they would reduce the E variance and they would move the within cluster predictions up and down.
Oh, so what would you say is the best definition for that fixed intercept? Conditional mean of the cluster means?
I think once predictors are involved, it's easier to think of it as like it's the expected outcome for the reference cluster and the reference person once predictors are involved. I think that's easier. At this stage, I tend to talk about it as a mean of cluster means because we don't have anything else to add to the story yet.
That's true, yeah. Okay, got it, thank you.
Thank you. All right, other thoughts or questions? Hit me.
Talking about the reference school, using school as a cluster. We're not talking about the specific school, but we're talking about a school that has a specific characteristics, right? Because as you're doing reference, I'm thinking about when you have dichotomous variable where something is referenced with other group. But in this case, we have a lot of schools. And the reference school is not really a school, but actually just that a cluster with a specific characteristic.
Yes, yes. Yeah, thank you for making that distinction. Yeah, so it's when I say like reference school, I mean at the reference value of the school predictors, not like school 182 as a specific unit.
That's where I'm a little confused.
Okay, that's where you were going with that. Yes. Language is hard, right? Everyone talks about statistics as like being math and coding, but the language that around it is like these subtle differences mean something. It can be very tricky. Yes. So a school of a reference type and a person of a reference type, like where type is determined by what predictors you have in your model. Can we agree on that one?
Sure.
Okay, cool. And like I often, I will write that out in a paper, like this is for the reference school, colon, who has this characteristic, comma, and for the reference student, colon, like who has this characteristic, and this characteristic.
You're boring and clear, thank you.
Boring and clear, exactly. And once I have that giant convoluted sentence out, then the rest of it's for the reference. Like I define it once and then just let it sit until it needs to be redefined somehow. Yep, words. All right, what's next? Oh, design effects, excellent. And it's only 1:08, we got time to talk about them today. Yeah, so this is something that I didn't talk about at all in the longitudinal class. It isn't really used in that context, but it's often used in the context of cluster data to do power analyses in particular. So a design effect expresses how much the sample size needs to be adjusted due to clustering. I can say this in a much more direct but sort of profane way. It tells you how screwed you are by your dependency. That's what it tells you. So this is the technical definition. How much the variance differs under a given sampling design relative to a simple random sample. So if you polled students from only one school, for instance, as opposed to pulling them from multiple schools, it is computed as follows. 1 plus, and then in parentheses, the level 1 sample size per cluster, so like the number of kids per school, for instance, times the intraclass correlation. So effective sample size then is whatever you started with in terms of the actual number of observations you have divided by this design effect. So it reduces how much information you have. Essentially, it's an indicator of how much reduction in information there is because of clustering. And if you look at how it's computed, it starts off at 1. So a design effect of 1 would mean there's no design effect, right? You get all of the power that you have. But as soon as this intraclass correlation moves off a 0, then you introduce a penalty factor. So only truly 0 intraclass correlations would mean that you don't have a design effect you need to worry about. But then you do later on as the random intercept variance comes back. This is a very simplistic formula that uses like the average of the cluster sizes. Like if you have a different number of clusters or kids per school, for instance, you need to weight that somehow. The textbook talks about that a little bit if you're interested in those things. Well, here's some examples. So let's say that I have 5 patients from each of 100 doctors and an intraclass correlation of 0.3. So that'd be kind of a large intra-class correlation, but there's not a lot of people per doctors. So the patient design effect in this case, if we put the math in here, 1 plus 5 as the number of patients per level 2 unit minus 1 times the intra-class correlation is 2.2. So if I feed that into the formula, I don't have power for 500 people. I have power for 227 approximately. Because people are partially redundant. That's why. We don't have as much unique information as a sample of 500 would expect. So the redundancy factor is expressed by this design effect. That's just a hypothetical. Like if this was my design, I recruited 100 doctors and I asked them to find 5 of their patients each. I have a sample of 500. But in reality, in terms of the amount of unique information those 500 patients are giving me, it's more like 227.
Is that why I think IRT needs such a exorbitantly large sample? Like they need like 3,000 or whatever? Because what you think of the design effect, it just drops it down so far that it's hard to say anything.
The modal IRT analysis completely ignores all sources of clustering.
Yes! I'm not saying that we should. but-
All of them. So, no, the reason that IRT models require a lot of people is because of the combination of a link function and latent variables. And the more items you have, the more parameters you're estimating. And there's usually between 1 and 3 parameters per item. So if you need a lot of items to get to a good level of reliability because your items are binary and they don't have a lot of information, then that's a lot of parameters and it takes a lot of people to estimate all those parameters. There is a limited literature on what happens if you ignore clustering in multi-level IRT. I would say that there's more stuff on that has come out in recent years because people can do that kind of work. So if that's something you're interested in, that might be something to think about for research down the road. One of my former students did a master's thesis on this topic and found at least in some cases it didn't make much difference in terms of the IRT parameters, but it did make a difference in terms of their standard errors, as you might expect. But if all you're doing is using the parameters to score, like sell some thetas, then the standard errors of the parameters wouldn't factor into that anyway. So people might be able to live with that. It kind of depends. But, all right, so this is not so bad. So what this would mean in practice is that if you did a power analysis and your power analysis magically said that you need 227 people for power for whatever, if you know that you're going to have to use a clustered design, you got to go find 500 people instead to have power for 227. That's what that would mean. Here's another situation. What if I only have an ICC of 0.05? There are recommendations floating out there that if your ICC is 0.05 or lower, it's fine. You don't need to worry about it. So I put this in here on purpose. Let's say that I have 20 students from each of 50 schools. So bigger clusters in this case, but less dependency. Yep, it's cut in half again. Yep. So if you think about it, like the upper limit, if I had an intra-class correlation of 1, then essentially what I have in terms of power is at the number of level 2 units. Because an intra-class correlation of 1 would mean everybody from the same cluster gave the exact same answer, as they're all like copies of each other. And so really what I have is 1 answer per cluster, and that's what my power would be based on. That the other extreme would be an ICC of truly 0, in which case people have nothing to do with each other, and my power is based on the overall number of observations instead. So somewhere between best case scenario of ICC of 0 and worst case scenario of ICC of 1 is how you would locate this. So this is something that you would probably use to predict power and make a plan for a study. You might report it after the fact. Do you see design effects reported in your literature?
Yeah, I knew what it was talking about, but I didn't know exactly this formula. But yeah.
There's a couple different variants of the formula, but I think they're all getting at that same idea. It's like how much harder do you have to work to overcome the clustering? Yep. So if you wanted to improve your power just recruiting more students won't help you as much as it would if all you had was students. You'd want more schools, actually. Thoughts? No?
I was just
Yeah, question
attempting
face.
to do some quick math in my head, so if you only had a sample of, say, 5 students from each of the 50 schools,
Mm-hmm.
then that'd be a 1.2, and that would be around, let's see,
It's better.
that's like, yeah, my brain's 6/5.
Well, I'll carry your point.
Down 8:30. So I can see if you had a very small sample and small thing and a small ICC.
Yep.
Maybe you can say okay.
Maybe.
I didn't say definitely. I said maybe.
What would be optimal is 1 student per school. From this perspective, that's optimal.
Well, yeah, because then
However, which student is going to represent that school? Right, you
it's
better get the
random,
right
therefore
one.
It doesn't matter, right?
Like a spelling bee or something, right? We can only send 1 person to the city contest.
Mhm.
Yeah, I threw the spelling bee in 5th grade because I didn't want to go to somewhere on a Saturday. I'm not proud of it, but I had priorities. The person who won really wanted to go, though, so I was happy for her. She can have that. So, in these data, we have an average of 19 people per school. So then that creates, rather than 3566 is my original design effect, I have, or my original sample size, excuse me, my design effect is 5. Yeah, so I have a 5th as many students as I think I do. Now 712 is still pretty good. And 191 is still pretty good for the number of schools. That's unusually large. So I have this in here. We've hit the main points so far, but there is no safe value of ICC to ignore, not even 0.
Lisa, now that we're talking about sample sizes in your experience, what's an acceptable level 1 small? What's an acceptable level 1 small sample size?
What's acceptable at level 1?
Yes. What's the minimum,
Well,
especially?
2 at a minimum. That creates a cluster. I do get this question a lot. If you have singletons, like if you did have 1 child per school, you can keep them. They can go in the models. However, they count at the school level in terms of their variance because they are the school at that point. So your interclass correlation could be slightly inflated in those cases if you have a lot of singletons because all their variance goes up to level 2. Did I answer your question? Oh, 2. What would be good?
Yes, in your experience.
More. More is good.
That's your answer to everything. Just more.
Unless you're from some of the EPLS data sets that have millions and millions of cases, then you need less. So,
That's not your field.
yeah, no, it's not. No, I mean, at an extreme, if you're doing dyadic data analysis, let's say you're studying like parent-child pairings or twins, right? There's a lot of people who do genetic research using twins so they can try to tease out what's heredity versus environment and all those kinds of things. How are you going to get more than 2 if you're studying twins? That's the upper limit. So, like, you do the best you can, I think. In a lot of cases, you're pulling whomever you can. And so it's like if there's only 5 people in that school, then you can't get more than 5. But I also don't think it would make sense in most cases, except for your millions aside, to only pull 5 from every school. Like if you have access to more, it's usually more work to add another school than it is to add more people in the school. So it's like if you're already there and doing the testing, get everybody you can, would be my advice.
Yes, thank you.
Yeah. So if you're interested in people level variables, get as much people as possible. If you're interested in cluster level variables, get as many clusters as possible. That's my answer for everything, more. Yeah. So an ICC of 0 becomes greater than 0 after you add in-person predictors because of the way it's made. And I don't think that's in this slide deck. Oh, yes, it is. It's the next one. It's like I knew this was coming. So I would say design effects are going to increase once the random intercept variance increases, so just plan to do a multi-level analysis. even if that's not your question. I can't tell you how many workshops I've taught where someone said, well, I don't have a multi-level question. Like, yes, you do, because you have multi-level data. You have to respect that, even if you don't care about the schools, they're there. So we want to address cluster dependency or correlation among the residuals of the people from the same clusters because of their effect on the standard errors of the person predictors. So even if you don't care about clusters and you only care about people, to get the right answers about the questions about people, you got to factor in the clusters. So there are various ways to do that. Contextual effects is another reason. So just as we think about, like in this case, language is the outcome, and language is 22% schools, if I put in some other person level predictor, it's likely to be at least some percent schools too. So each person predictor is not just a person thing, it's also a cluster thing in most cases. These people are not randomly assigned to their clusters. So in the case of twins, so just to give you an example, there's a particular statistic called heritability, and it is computed as twice the difference in interclass correlation between monozygotic twins and dizygotic twins. So it's used in that context. And it actually can go negative if the interclass correlation is higher in dizygotic twins. So it's not a great measure, but just as an example, people use it for that kind of thing. So if you have twins, they're going to have something in common. And that is probably going to be true whether that thing you're thinking of is an outcome or a predictor. So you'd want to have like twin level stuff and then pair level stuff in the same way that you want to have kid level stuff and school level stuff. So just doing a single level regression would ignore all of those issues. Clustered sampling correction can fix the SE part. That's an option that you can add in most software, but it does not solve the contextual part, meaning extra relationships need to be there in your model at the higher levels, even if it's just a person predictor, because it's also a cluster predictor. So we're gonna stick with that. All right, how are we doing? Thumb check. Up and sideways, okay. That's good. Good, good. Any that you want to hear again or talk more about?
So do people use the sample size in reverse to see how many they actually need to get to a particular sample size that they know they have effect for?
Yep.
So
Yep.
if they want 1,000, they say, okay, let me work my math in reverse.
I have, in chapter 13 of my book, I have on the Piles of Variance website a spreadsheet I made to do power analysis anticipation using interclass correlations and cluster sizes. So yeah, that's exactly what I would do, is like try to figure out what a reasonable range of ICCs would be for whatever you're studying, a reasonable range of cluster sizes, and then you can put them in combinations. And so my power analysis would say something like, you know, given this range of expected ICCs and this range of expected cluster size, my power to detect, you know, an effect of R greater than point whatever is between this and this. Like, you can just sort of give them ranges rather than say you know exactly what's going to happen. Power analysis is a lot of creative writing, though, to be honest with you. So why is ICC of 0 not safe? Here's why. It's a consequence of how it is estimated. It is not actually just between cluster variance if you think about what is observed. So this room is a smaller class, but we can do this anyway. Let's say that I randomly assigned this class of 9 people into 3 groups, okay? And I asked each group to compute a mean height for the group. Now I randomly assigned you, so there shouldn't be that many differences in height, right? But is it going to be exactly no difference in height across the groups? No, it depends on which of you happen to be there, especially if there's only 3 people per group, right? You'd expect more equivalence the more people that you get. So in that case, I would want to try to figure out, well, how much of the variability in these mean heights is just because of like noise versus signal? And the computation of random intercept variance tries to do that. So it starts with whatever the observed variance is, meaning like literally compute the mean for each cluster and then see what the variance across those cluster means is, that's observed. And then know that that is partially due to true signal. There are real mean differences across clusters, and partially due to like which random people you have in your cluster. This part is the noise right here. This part is the signal. So noise is level 1 residual variance divided by the average number of people per cluster. That's the noise factor. So then what happens is the program says, okay, well, I computed the means of the cluster means, I computed the residual variance thing, so now I can figure out how much is true. So for example, let's say that these are my numbers. I have an observed variance across my cluster means of 4.65. I have level 1 person variance of 7.06. Like these are from an empty model, let's say. And I've got 4 people per cluster. Cool. So that means in this model, my true between cluster variance, tau squared sub u0, the variance of the random intercepts at level 2, would be 2.88 if I work through this math. Let's say that I then add in a bunch of person predictors and I do a wonderful job in reducing my level 1 residual people variance down from 7.06 to 2.17. Yay me! No. Now my true between group variance is 4. So this is what can happen and will happen because of the way these things are computed, particularly in smaller clusters. So this residual variance gets down-weighted in larger clusters, but in small clusters you'll see this make a difference. So even if your ICC starts out at 0, random intercept variance will increase as residual variance decreases. It has to, they're yoked together. So, bummer. All right, ICC2, do we have room for one more ICC in our heads? I bet you know this one too. Yep. So I call this the reliability of the mean, that it has a special name of ICC2. This is much more common in some contexts than others. Like I don't ever see this in longitudinal data, although they could compute it. So here's the same example in numbers that we're working with. This is computed the same way as the intraclass correlation we just talked about with one tiny change. Where we had level 1 residual variance in the denominator, it is now itself divided by the level 1 sample size per cluster. So this is supposed to give you the reliability of the cluster mean. It is analogous to Spearman-Brown reliability in classical test theory land. It assumes that people are interchangeable. Spearman-Brown reliability assumes items are interchangeable in the same way. Parallel, in fact, equal loadings equal error variances. So in this case, we have a fairly high ICC2 because we have a lot of people per school and a reasonable amount of differences between them. So this will often be used to talk about like whether or not you should do level 2 anything. Like, do you have enough level 2 information to say that you have a reliable intercept to predict? So if you think about this as like a psychometric measure composed of items as people, then it starts to make more sense why we would want to see this. Yep. So ICC2 is what this is called. All right. Question?
Lisa, what happens if we have a slow ICC2, let's say 0.4, for instance? Doesn't mean that the cluster mean differences are not reliable, so they are not like true differences?
Well, it could mean that. So the problem with, like, there's also a slope reliability that I'll show later that you're probably thinking of in this context as well. The problem is that you can have a low intraclass correlation too because you don't have a lot of variability in your cluster means in the first place. So like if you just happen to have a construct that doesn't have a lot of like variance like you have, right? There's not a lot of variance across states in people's vocational aspirations. It's not a strong signal. It doesn't mean you can't try to predict it, but just in the same way that you might expect a test that has low reliability to not relate to other stuff very well, like this could be one of the reasons if you have low reliability. But it may not be something that you can change.
Oh, okay.
So like if I continue this analogy of classical test theory, how do you make a test more reliable? Add more questions. What kind of questions? More. No, doesn't matter if they're good. More is the answer. Because the formulas for Spearman-Brown reliability and alpha reliability have the number of items in there. More is better. What if they're crappy? Bring them all in. More is better, right? So from that perspective, I need some more kids per school. More is better. Well, what if I have all the kids in that school? Or I have all the people in that twin pair? Like, then what? So you may just not have a lot of cluster signal, or you may not have essentially a lot of power to find it. Yeah. But
what if the sample size of our cluster is not the
Then you'd have to find some way of representing that in the formula. There's an R package I found that does this that I think you can also do like separate versions, like keep these numbers the same, but then have separate versions here and then like compute some kind of average. Like there's various different ways of computing it that would take into account differences in cluster size. I might be tempted to throw like the smallest one, the mean, and the largest one and report those three numbers just to see like how much variability there is in the consequence as a function of what your cluster size is considered to be. It's not something I know a whole lot about because in my world they don't care. Like that's not something people report for longitudinal data very much. There's also a statistic called RWG or ROWG that's used in this context. I don't have anything about that in here, but that I can tell you more about that if anyone cares. Let's put it that way. All right, here's another thing that we can do to talk about cluster differences. And this is what I would do to talk about it in more lay people terms, right? So like people who are not familiar with multi-level models, like let's say that you're explaining cluster mean differences to your school board, right? And they didn't take the multi-level model in class. So you got to find ways to get to them and make them understand what you're talking about. I hate confidence intervals normally. Like the kind around fixed effects, I just hate them. I actually have to read my own slides word for word when I get to that point to avoid screwing up the definition because it's so non-intuitive. I love these ones though. These intervals make sense. So this is a different kind of confidence interval than you've ever seen, I'm guessing. Because what we're trying to do is describe what the range of the cluster means is predicted to be given the amount of random intercept variance we estimated in the data. So, for example, 2 different intervals are possible from this empty model that has a fixed intercept, a random intercept variance, and a residual variance. So around the fixed intercept of 41, I can compute a typical confidence interval. So I have my Z critical value for how much % confident I want to be. 1.96 would be 95% confident. The estimated standard error for the fixed intercept as the thing that is creating the interval. So that result would be 40.4 up to 41.7. That number describes the expected fluctuation of the sample mean across repeated samples. Like how precise is that 41? The standard error tells us on average how far off the mean would be in other samples, like from the true population mean. So this interval that we would typically compute, that I hate, describes how precise the fixed effects are, okay? That's not what we're doing. In contrast, I'm still going to start with the same centering point of 41.08 as the fixed intercept, but now I'm going to put around it the square root of the random intercept variance. Crossover event with the intermediate class. What do we call the square root of a variance?
Standard.
Close. Standard starts with a D. Yeah, deviation. So what I'm doing is essentially saying plus or minus 2 standard deviations, where a standard deviation is defined by the variance of the random intercepts that was estimated by the model. So now my range, if I work through the math here, is 32.8 to 49.4. That describes for 95% of my clusters what the expected range is in their scores. So now if I'm an administrator, I can say, so you're telling me some schools are going to do as bad at 32 and some schools are going to do as good as 49 on average? Yes. So that makes the idea that we have 22% school mean differences variance, I think, a lot more concrete when you put it into the metric that the outcome is in. Like, how big is that?
And that's because we're using the mean of the cluster means, not the original data, that we can say this sort of stuff. I shouldn't say original data.
Yeah, so
I should say because we are using the means of the clusters, that's telling us the spread of the clusters, not the spread of the original.
yeah, we're not trying to figure out how much the sample means would vary.
Right.
We're trying to figure out how much the clusters vary in a sample from each other and putting it in a metric that is the same as the original outcome variable. So if my school on average, if I'm in the 32 school and someone else is getting 49, like that's I think that's, I don't know the scale of this variable, but I would assume that that's a big difference. 15 points is a big difference. So I would do, like, why not report all of them, right? Report ICC1, ICC2, random intercept confidence interval, why not? Cover all your bases. Oh, that's good. All right. Yeah, it is. I know. I'm
No,
like,
I'm
oh, this is
review-
a transition
review
point.
number 3.
I know.
Why you do it.
Who here knows what a likelihood ratio test is? Okay, put your hand up. She's like, no. The difference in -2 times log likelihood between nested models, where the degrees of freedom for the test is the number of things you added. You compare it to a chi-square distribution and see if your model got better or not better. Now, does that sound familiar?
If you have generalized, hopefully.
We did that in generalized to talk about adding predictors to generalized models. We did that in generalized to talk about adding stretchy factors to count data or to binomial data. We did that to think about whether each kind of multivariate outcome needs a different variance and covariance across pairs. We did that in longitudinal for lots of stuff, and we're going to do it in here too. So you've seen this before in most cases, and if you haven't, you'll catch on real quick. So when we do comparisons of models to try to figure out what is needed, that's what we're talking about here. We're building models and adding stuff to them. We don't need to do any of what I just said if we're adding predictors to the model for the means as fixed effects. We can stare at the wald test p-values that come out of the output the same as usual. So you'll see estimate, standard error, t-test statistic, sometimes degrees of freedom, and then a p-value. We can do that for fixed slopes all day long, no problem. For the model for the variance, though, in deciding whether we need a random intercept variance or whether we need a 2-level model or a 3-level model, that question boils down to, do we need 2 extra piles of variance besides residual at level 1 or just 1? Any kind of question that has to do with what should be random in these models, we need to do some kind of assessment of relative model fit using -2 times the log likelihood. We cannot use the wald test p-values because wald tests assume a 2-sided symmetric sampling distribution, which is not going to be true for variances, even more so the closer they are to 0. There's a very boring article that's very useful on your list about this if you're really into like boundary conditions and statistics. So, not to be mean, boring is good though, it means it's clear. So, it's a complicated topic, point is at the end of the story. So we're going to do, and this is another thing where we can re-go over this next time as needed, since it's the second week of classes and you're like, I don't know what I used to know. It's gone. It's dormant. It's going to come back, though. It will. I promise. So model fit is indexed by something called a log likelihood. Essentially what happens is that you pick a distribution for your data. Given the model parameters, you calculate something called a likelihood under that distribution. It is a height. So given the model parameters and my data, how tall is my outcome? And how the model parameters are selected are the ones that make everybody's height collectively the tallest. People are assumed independent in standard regression, and so rather than multiplying their likelihoods together, we can add them if we take the natural log. So for computational purposes, logs solve a lot of problems. That's why we call it log likelihood. So each person would have their own contribution to the log likelihood. The tallest set of parameters wins. And then we can say, all right, look, if we add these new parameters, how much taller did the model get? And taller is defined by a chi-square distribution as a reference point. This gets a little trickier in this class because there's another kind of maximum likelihood that we're going to use. And it's called residual or restricted maximum likelihood, or I will say this as REML in this context. When I used to have the Zoom transcript, it would always say Rambo or some other combination for REML. So in this, I will switch from saying ML to ML in REML. That's how it's pronounced in this weird context. Also, Zoom thinks fit statistics are fish sticks sometimes. So that was probably my favorite one that I've seen. Yeah, but so in these models only, we're going to be using REML. Models that have conditional level 1 residuals, we're going to be using REML. So how the log likelihood will adapt, we'll talk about in a few weeks, but basically rather than having what is the height of each person's data, it is what is the height of each cluster. And people are treated as multivariate observations within a cluster. So it's the height of the group that gets added together under the assumption that groups are independent. So what we get out of this index of model fit is either going to be log likelihood or that value times -2. That seems really weird to do that, but it's because the difference in log likelihoods times -2 is supposed to follow a chi-square distribution. And knowing that we're going to have to take that difference times -2, some software anticipates that for you and spits it out that way to begin with. So SAS and SPSS mixed, some parts of R, but not all, will give you -2 log likelihood directly. And in that case, the -2 flips the difference. So -2 log likelihood is badness of fit. It's like shortness. Log likelihood is height, -2 log likelihood is shortness. So we want models that make the height taller and the shortness lower. And Stata Mix and M+ and a few parts of R will give you log likelihood instead. So you got to figure out which one you got, and then we can figure out what to do with it. So a likelihood ratio test is also known as a chi-square test in SEM parlance. It is known as a deviance test in multi-level modeling as well. It is just the straight difference. So fewer minus more is the order that has to be to keep the result positive. So we take -2 log likelihood for the model with fewer parameters minus what it is in the model with extra parameters. The result needs to be positive. Then we figure out how many parameters the models differ by, and we have that as degrees of freedom. So we compare that then to a chi-square distribution, and you can get a p-value. So I use the function chi-dist in Excel to do this. There are functions within R and Stata to do this. I wrote a routine in SAS that does this. Don't want to talk about that. So basically, if you improve your height by adding one thing, if your -2 log likelihood goes down by greater than 3.84, that's the cutoff for 0.05 for 1 degree of freedom, then your model is better. So if you add stuff, you have two choices in what can happen. What do you think they are? Stay put is not a choice. I would say if you add stuff to your model could get better, right? Or not better. In terms of -2 log likelihood, it cannot get worse. Other things can, but that one cannot. So if you add parameters to a model, then your fit according to -2 log likelihood should get better or not better. Those are your choices, and that's how I would say it. If you take things away, then you have two different choices. Worse or not worse. And there's no right way to phrase it. Sometimes one way makes more sense. So the test as to whether or not you have, say, a single factor in your data set is a worse, not worse question. Because you start with a model of all possible correlations, you compare it to a model where the correlation pattern is predicted by the factor loadings, and then you see how much shorter your data got with the factor loading version. In this class, it's almost always going to be a better, not better. We're going to add stuff and see if it helps, because there's no answer key to come back to for cluster data in the way that there is for test data or longitudinal data. So. And we'll leave this bullet for next time, because it's Tuesday, which means I say, thanks for being here and see you Thursday. That's what I say. So any questions before we call it a day? We're good for now? Good for now? All right. Well, thanks for being here, folks. I will see you all Thursday. Go enjoy some lovely weather outside. For once.